Welcome to the last video in the 3-video series on the simplest radical form. So here we go. Let's talk about rationalizing the denominator. Earlier, I mentioned that I do not like fractions with radicals in the denominator, and in fact, nobody really cares for those. So we are not going to express our answers that way. We are going to instead rationalize the denominator whenever we have a radical or an irrational number left in the denominator. When we've simplified everything as much as we can, then we're going to use a technique to make that denominator rational again. Okay, so let's take an example. I think I'm up to example 12. So the example I'd like to use is the square root of 2 over the square root of 7. Even if we were to put that under one radical and have the square root of 2/7, that doesn't give us anything. However, if I think about what do I need to multiply that square root of 7 by to get a perfect square under the radical, it turns out that if I multiply by 7, okay, the square root of 7 that is, and I do the same thing in the numerator, I will have in the numerator the square root of 2 times 7, okay, because the indexes were the same, the indices were the same, I can do that. And in the denominator now, I have the square root of 7 times 7, a perfect square. So the square root of 7 times 7 is 7. Square root of 7 squared is 7. But avoid temptation. Do not try to cancel the 7 from the numerator and the denominator. The 7 is fine, it's an integer, but the 14 is under the radical. You cannot cancel there. Okay, let's make this a little bit smaller and move it out of the way. All right, and let's go for another example. What happens if instead of a square root, you actually have a cubed root that you are working with, a cube root? So if you were looking at the cubed root of 5 over the cubed root of 3, okay? In our previous example, we wanted a square root or a perfect square under the square root. Now that we have a cubed root in the denominator, which we're trying to get rid of, we need to get a perfect cube under that index of 3. So I have here, in effect, a 3 to the first power. So to get a perfect cube underneath there, I'm going to have to multiply by 3 squared. If I do it, multiply in the denominator, I have to do the same thing in the numerator. So I'm going to multiply the numerator by the cubed root of 3 squared and the denominator by the cubed root of 3 squared. Because I have the same indexes all over the place, I can rewrite this way, okay? Bringing them all under the same cubed denominators. Could I do the whole fraction at once? Yes, I could. But for right now, I'm doing it this way. 3 to the first times 3 squared, okay? So on top I have the cubed root of 5 times 9, or 45. In the denominator I have the cubed root of 3 cubed, or I have the cubed root of 45 over 3. Okay? Also, once again, do not try to cancel here. All right? Yes, 3 goes into 45, I'm aware of that, but the 45 is stuck under the cubed root symbol, so you cannot cancel. Okay, and the final technique for simplifying radicals that we're going to use involves not rationalizing the denominator, although that is very useful. We're going to just move this whole thing out of the way. And the next thing we're going to be talking about is this. it is reducing the order of a radical. And in fact, this is such a different topic, I'm going to start it out in a different color. Let's redo that, get rid of those. Okay. So we're going to be reducing the order of a radical. Okay. So my first example for this, which will be example what? Let's see. I was up to 13. This will be example 14. All right, example 14 is this. What if someone asks you to take the sixth root of 8? No idea what that is. Okay, so let's see how we could look at it differently. The sixth root of 8 could be rewritten as the sixth root of 2 cubed. Doesn't seem to be going anywhere fast that way. What if we rewrite that radical as a base with a fractional exponent? Okay, remember the exponent in the radicand moves to the numerator, and the index moves to the denominator of the exponent of the radicand. Okay, and that looks rather messy. I'm going to erase all of those arrow marks. Okay, so that's the way it is. But take a look at 3/6. We know how to reduce 3/6. It's equal to 1/2. Now if we express it back in radical form, 2 to the 1/2 is the same thing as the square root of 2. And you've seen that before. You've seen that a lot. You've worked with it a lot when you were working with special triangles. That's the hypotenuse of a very special triangle. But we're not doing geometry right now. So let's return to an example 15. Okay. This example is going to be rather more complicated. We're going to take a ninth root. We're not just going to take a ninth root of a single thing. Let's take a ninth root of 8 x to the 6th. Let's start there, and we'll get a more complicated one in a minute. Okay, so in this case, you would have a ninth root of 2 cubed. That's how 8 can be rewritten. We're going to leave x to the 6th as it is for now. But let's take all of them now and rewrite this entire expression with fractional exponents. So the ninth root of 2 cubed would become 2 to the 3/9. X to the 6th under the ninth radical would be x to the 6/9. And that would be equal to 2 to the 1/3 as we reduce those fractional exponents, and x to the 2/3. Okay? Can't reduce those fractional exponents anymore. Let's see what that would look like if we put them all back under the radical. Notice the denominators here are the same, so they can go back under the same radical with that index of 3. And 2 is raised to the first power, so it's just 2. X is raised to the second power. Okay? So that 2 comes right under there. And you're done. Still not perfectly, if you consider integers perfect. Not perfectly simplified, but much more simplified than when we started. Ooh, a little echo effect there. I may have to play with that. All right, let's do one final, slightly more complicated example. So let's kind of move this out of the way. And let's go with a number 16. Okay, still reducing the order of the radicals, so I think I'll stick with blue. What color is this? Green. Okay, let's do the ninth root of 125 x cubed y to the 18th z to the 6th. Yeah, we'll just leave it z to the 6th there. Okay, so what is this equal to? Let's get some integer exponents and everything under that radical before we go any further. So 125 is equal to 5 cubed. We have x cubed, well, everything else is integers, isn't it? So we have them all as integers. Let's convert everything to a radical form. Or excuse me, not a radical form, but a base with a fractional exponent. So 5 to the 3/9, x to the 3/9, y to the, ooh, look at this one, an improper fraction, 18/9, and z to the 6/9. They all have 9 as the denominator because we are looking at the 9th root, but the exponents that were under the radical became the numerator, so that they have some different exponents. All right, so let's see how we can reduce those fractional exponents. We keep the base of 5. It becomes 5 to the 1/3, x to the 1/3, y squared, and z to the 1/3. Wow. Would you look at that? We have a integer exponent that is not going to be under a radical by the time we finish. Okay? So all of these others still have fractional exponents, and it turns out that their denominators, let me use something else to indicate that, their denominators here, we have 1/3, 1/3, 1/3. No, we do not have 1/3 here. Look at this. Ooh, be careful. There, z has a 6/9. If we are reducing that, it is not going to be 1/3. It is going to be 2/3. Because 6, come on, 6/9 was our exponent. If we divide both the numerator and the denominator by 3, we should get 2/3. Okay, that makes a big difference in our answer. We still do have, however, the denominators all the same, 3, 3, 3. So they are all cubed roots. They will all go under this cubed root. And the numerator of 5 up here is 1. So it goes in there underneath the radical. 5 to the 1/3 becomes the cubed root of 5. X to the 1/3 becomes the cubed root of x. Z to the 2/3 becomes the cubed root of z squared, because that 2 in the numerator comes down under the radicand. But then we have that y squared. It's not under the cubed root. It can stand alone outside here. And that's the final answer. That's all I have time for. I will see you tomorrow on Blackboard Collaborate at regular class time.